And welcome to Chapter 3, which you can take a look here. Chapter 3 is going to be about justification and similarity. We're going to be looking at similar shapes in this case and being able to justify. We're going to more specifically talk about being able to back up your reasoning with mathematical proof. Okay, so we are going to get into that. We are skipping Lesson 3.1.1 and we're going to go straight into Lesson 3.1.2. Which, if you notice, how can I maintain the shape? We're going to talk specifically about what similarity is and kind of the properties of it. So far, you've studied several figures that appear to have exactly the same shape, but not necessarily the same size. But how can you know for sure that two figures have the same shape? Today, we're going to focus on the relationship between the lengths of sides of dilations by enlarging and reducing figures and looking for patterns. So similarity is based on this idea of a dilation, where you take a shape and you either enlarge it or you reduce it. Okay, either one is called a dilation, just like when you dilate your pupils when you go to the eye doctor. Same idea. Or another example would be like a matchbox car. A matchbox car, I don't remember exactly, but I want to say it's like 1/32nd or 1/64th of an actual car. They go through and they take all the measurements, and then they shrink all of those measurements down by, like I said, by a factor of 1/32nd or 1/64th, whatever it is, in order to get a matchbox car. So if you notice in problem 3.11, notice it says find your work from problem 3.5. That was from 3.1.1, so ignore that. But here's the picture that you have here. And what I want you to notice is I want you to take a look in this case at both the coordinates and then the side lengths as well. So obviously, A and A prime, right here, we're at the origin. That's kind of going to be what's called our stretch point, okay, if you will. If you notice, A prime, B prime, C prime here is just a bigger stretched out triangle of the original one. They just enlarged it, okay? So B, if you notice, has the coordinates 3, 4. B prime has the coordinates 6, 8. Okay. C has the coordinates 3, 0. C prime has the coordinates 6, 0. Okay. And then if we go through and we take a look at side lengths, that means this length is 3. That means this whole length right here for the bigger triangle is 6. This height right here, this triangle, is 4. The height of this bigger triangle is 8. Okay, so if we're taking a look at a couple of different things here. So notice what it says here. What is the relationship of the corresponding sides? Well, if you notice, the bottom side and then is basically just stretched out to get from A prime, C prime. The vertical side is stretched to get to B prime, C prime. Okay, and then the hypotenuse of this triangle, A prime, B, or AB, is stretched to get AB prime. Okay, so you have all of those different things. What I want you to notice is if you take a look at the coordinates to go from C to C prime, notice all they did was double those coordinates. To go from B to B prime, all they did was double those coordinates. To get from side lengths, I went from a factor of a side length of 3 to a side length of 6. All they did was double. From 4 to 8, they doubled. Okay? And so what I want you to notice here in part D, notice it says, could you get the side lengths by adding the same amount? So notice, if I wanted to go from 3 to this whole length of 6, I would just have to add 3 to it. But if I took this side length and I added 3, I do not get 8. So the point, and it's a really big point that they're trying to get here in part D, is they're trying to get the idea of when we go from one shape and we go through and we dilate it or we stretch it, we multiply side lengths by a certain factor. Okay, in this case, it's a factor of 2. I'm doubling everything. We do not add. Okay, we are multiplying by a factor. And so then, if we went through, and I'm going to kind of skip this part of it just because we're still working on it, but I could go through and I could find the length of this hypotenuse because I know this is a right triangle because we're on a grid here, so I know that that has to be a right angle right there. Same idea for the bigger one. I know that this is also a right triangle. And we could do the Pythagorean theorem to find this length, okay? 3 squared plus 4 squared would give me this side length squared, ultimately, if you went through and you did that, what you would find is the hypotenuse has a length of 5, which now, if I wanted to, I don't have to go through and redo this and have a 6, 8, and then figure this out. I know that this enlarged figure is just twice the size. Therefore, I know that the bigger hypotenuse then is going to be a length of 10 because of our what's going to be called a zoom factor or scale factor of 2. So then down here in this last one, it says Monica dilated the original triangle to get a different one, and she knows that A prime, B prime, that segment is 20 units long, or double prime, excuse me. So she took this original one, and now it's a length of 20. So the question is, how many times larger is that? Well, if our original length was 5, and our new length is 20, we know that in this case, it is 4 times larger. Okay? That is our scale factor, or that would be our zoom factor, okay? So on and so forth. So then, if we move into the next portion, so similarity here. An important aspect of dilation is the fact that the shape of a figure does not change, even though it's the same, its size might. Okay? This is because dilations do not affect the angles while they change the lengths proportionally. I'm going to go through and highlight that because that's a really important part of this entire chapter. So let me go through and let's highlight that piece right there. Dilations do not affect the angles while they change the lengths proportionally, meaning by a certain zoom factor or a certain scale factor. Okay? So, I'm going to skip here to part B. When two figures are related by a series of transformations, they are called similar. And right here, similar figures can be created by multiplying each side length by the same number. That number is what they call here the zoom factor, or you might, like I said, you might know it as the scale factor. Okay, how many times bigger or smaller is something? You may have used a zoom factor before if you used a copy machine. We already talked about it with like dilating pupils. We talked about it with the scale factor or zoom factor of Matchbox cars or toy cars, things like that. And the idea is it keeps the same shape, but it's a different size. That is called a dilation, and that's the concept of similar shapes. So if you take a look off to the side here, when we're now taking a look at, if this is the original and the height of this shape is 5 inches, 5 centimeters, doesn't matter, and then it's enlarged, so now that it's 5, the zoom factor in this case, the scale factor at which we are enlarging this, we are not adding 10, we are multiplying by 3, okay? And that's the idea of a scale factor, is how many times larger is it, not what can I add, okay? So that gives you an idea. So to give you kind of another idea behind this, this is just a resource page that goes with this. So if this is the original shape of something, we have to multiply every dimension that we have by that zoom factor. So if I were to take this original shape and let's say I only multiplied the height, this is what this looks like. It's no longer the same shape. This is now distorted vertically, okay? If I only multiplied the base here by something, here's what that would look like, where we kept the height the same. Again, it's distorted. It's not the same shape. In order for this to be similar, we'd have to multiply both the base and the height by that same factor. Okay, so just kind of a quick way to take a look at it. So now if we take a look here in problem 313, it says Casey decided to enlarge her favorite letter C, of course, C for Casey. It says to have each member choose a different zoom factor and then on graph paper enlarge it. What I'm going to do is I'm just going to do one of these so that you can take a look at it. And so let me go through and actually simplify this down. Let's go a little bit bigger than that. So let's say that we have this. I'm going to do part B where I'm going to double the side length. Okay. So as I do that, the first thing I need to do is figure out the side lengths of everything. So notice, first off here, we have the very top. We've got 1, 2, 3, 4, 5, 6. So this length is 6. This length is 2. 1, 2, 3, 4. This part is 4. This is 4. This is 4, this is 2, that's 6, and finally we've got a height here of 1, 2, 3, 4, 5, 6, 7, 8. Yep, total height of 8. So now, if I'm going to go through and try to enlarge this by a scale factor of 2, that means I need to enlarge every single one of these dimensions by 2. I can't just do one, I can't just do some, I have to do all of them. I'm going to start with the height because that's the biggest number that we have here. So I'm going to enlarge that by a factor of 2, meaning the height is going to go from 8 to 16. Okay, so I'm going to start right here. And let's say we go right here. So here would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There would be the height. The top and bottom then need to go from 6 to 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Same thing down here. I gotta go one more. Okay, then the next part, I'm going to go down here. Instead of that being 2, it now needs to be a factor of 4. 1, 2, 3, 4. Same thing up at the top. 1, 2, 3, 4. These all need to go then from 4 now to 8. And therefore, 1, 2, 3, 4, 5, 6, 7, 8. Same thing here. And then hopefully this should match up and be 8 as well. 1, 2, 3, 4, 5, 6, 7, 8. And there it is. So in this case, we took this original C with these dimensions that we counted, and we enlarged it by a scale factor of 2, meaning I doubled every single dimension. Okay? Up here, if I went to a scale factor of 3, I would triple all of these dimensions. If it was a scale factor or a zoom factor of a half, I would take half of all of these dimensions and make it half the size. If it's a zoom factor of 1, in that case, hopefully it makes some sense that you don't change it, and therefore that isn't identical in size and shape. Okay? But I wanted you to at least to see one and see the idea that all dimensions have to be changed, which relates back to the idea of this picture that we were looking at before. Okay? So if we keep moving forward then, in problem 314 here, notice it says what happened when the zoom factor was 1. Well, what I want you to take a look at is they add in now, let me do another highlighter here, they add in the concept of congruent, okay? So the two figures that are the same shape and the same size, okay, that is they have a zoom factor of 1, that is called congruent, okay? So if they're the same size and the same shape, then that's congruent, not just similar. And we're going to come back to that concept again as we move forward in this chapter and in this class. Okay. So notice here they say to compare the shapes when tracing, determine which shapes are congruent. I'm going to kind of skip through that part. I mainly wanted to highlight this idea of the same shape. It's a little bit hard to do this one when they all kind of look the same size, same shape. Unless you had patty paper to confirm it, it's a little bit hard to do. So I'm going to skip through that. So now we start to talk about equal ratios, okay, that idea of the zoom factor. So notice it says since the zoom factor multiplies each part of the original shape, that means the ratio of widths must be equal, okay? And same thing with the ratio of the lengths. So if we take a look, notice how they're comparing. The height was 24 compared to a height of 8, 8 compared to 16. So in this case, we have a zoom factor, okay, if you will, for my height. The zoom factor is 3. Same thing with the widths. The zoom factor is 3. So we're starting to get through that idea of ratios, that idea of proportions. If you remember back, we started working on these in chapter 1 and some of the warm-ups, and that's where this is coming from. This is now going to start to come into play a lot more. So now the question is, well, what happens though if this is not enlarged by a nice number? Okay, so notice the heights, if we compare those, it doesn't go in, 8 doesn't go into 20 nicely, okay, and then if I wanted to find the missing value. So what I want to do is I'm going to set up, just like they did here in part B, I'm going to set up the ratios. They should be equal, okay? So in this case, the ratio of 20 to 8, the heights, should be equal to the ratio of x to 6. Those two ratios should be equal to each other. And now we're right back to where we've been in the last couple chapters where we've just been solving these. Now I can take a look, and I'm going to go through and cross multiply. I'm going to multiply one diagonal, and that should always equal the other diagonal. Okay? So 8 times x gives you 8x, equal to 20 times 6 gives you 120. And now I have an equation that I can solve and come up with an answer for x to see what that actually does equal. Okay? In this case, it turns out that it's a fairly nice answer. I shouldn't say fairly nice, it is a nice answer. It turns out that x equals 15 for that dimension. Okay? But this is our concept when the zoom factors or the scale factors are not whole numbers. It makes it a little bit more difficult. So in that case, rather than you going through and dividing and figuring out what the zoom factor is, I'd rather have you get into the habit right now of setting up these equal ratios, because the zoom factor will not always be even a nice decimal. It's going to be something sometimes where you have to go through and round it, and I do not want you to round the zoom factors. I'd rather have you set up these ratios and solve it exactly. Okay, so just a heads up on that. All right, if we finish this one up, then this is, I believe, the last slide of this lesson. It says to use your observations about ratios to find the answers. Okay, so in this case, assume one triangle is 6, 7, and 10, another one's 3, 4, and 5. Are these triangles similar? So the first thing we need to look at in order to answer that question of are these triangles similar, we need to see if the side lengths have the same ratios. So smallest side length, okay, if we go through and set up those ratios, 6 over 3, that's a zoom factor or a scale factor of 2. If I go through and I take 7 and I divide it by 4, there's my next set of ratios. 7 divided by 4 is actually 1.75. If I set up my last one, I get 10 divided by 5, which I do get 2. And so if you notice, these are not all in the same ratio. This goes back to that idea of that picture of that child, okay? In order for things to be similar, all of the dimensions have to be enlarged or reduced at the same ratio. This is not the case, and therefore these triangles are not similar because they do not have the same ratios. Okay? So finally, in part B, they say if the pentagons here at right are similar, so they are telling you that they're similar, which means they are in the same ratios, then what are the values of x and y? So in this case, this one's a little bit nicer because they give you a nice ratio. We want to go through and take a look at what is the actual ratio. Well, notice we've got this 8 and 24. So that ratio of 24 to 8 means that I have a zoom factor or a scale factor of 3. So therefore, if I take 11 and multiply it by 3, that means x in this case will be a value of 33. There's that answer. And I can also go the other direction. Since I know that this has a zoom factor of 3, I can take this 18 and work backwards and divide by 3, which means that value will end up being 6. Okay? So if you're going from a smaller shape to a bigger shape, we're multiplying. Bigger to smaller, we are dividing in this case. So this one was a nice one because we had a nice zoom factor of 3. If this was not a nice zoom factor, then you should set up your ratios similar to, let me go back to this, what we did right here in part C. You would want to set up your ratios and solve for the variables instead. Okay? In this case, we didn't have to do it because it was a nice value. So last thing that I have for you here, this is a math notes box just talking about ratios of similarity, setting up ratios, zoom factors. I'm just going to go through and highlight a few things. Other than that, this is a good kind of summary of what's going on. And so if we take a look, a comparison of two quantities is called a ratio, and there's kind of 3 different ways that you can go through and you can set those up. Okay. Notice, here's the idea that you have in terms of setting up the ratios. They talk about ratios of similarity between corresponding sides in a similar figure. I'm going to kind of highlight that as well. That is called the ratio of similarity or the zoom factor. Okay. So again, right here, well, there are several names for that number. This text is going to call it the zoom factor. The scale factor is another commonly used term. Okay. To help indicate if the figure was enlarged or reduced, the zoom factor is written as a ratio, okay, of the new figure to the original figure. Okay. You always write it as a ratio of new to original. That's how you would go through and you would write that. So that's why in this case you would write it as 10/6 because that's your new shape compared to the original shape. So it has a zoom factor of 10/6 or 5/3, which means if you wrote it as a decimal, that'd be like 1.6 repeating. Okay. So just a heads up, it's always ratio of the new figure over the original figure. All right, to finish this lesson up then, your practice to learn for this is the 312 practice to learn, and I want you to do problems 319 to 323. You can skip the first problem 318 in that and not worry about that. Okay, if you have any questions on the lesson, you've got any questions on the practice to learn, bring those questions with you to class, and we will go over those when I see you in class. Good luck, everybody.